What is the purpose of applying feature scaling techniques like standard scalar in machine learning? Pipelines. A. To improve the performance of certain machine learning algorithms by ensuring features are on a same scale. B. To reduce the influence of outliers on model training. C. To prevent numerical instability and improve the convergence of gradient-based algorithms. D. All of the above. Correct. Many algorithms like KNN, SVM, and gradient descent-based algorithms perform better when features are on a similar scale. Features with vastly different ranges can lead to the algorithm giving undue weight to features with larger scales, distorting the model's decision boundary. Standard scalar helps normalize features to have zero mean and unit variance, ensuring all features have comparable scales. A. Improved model performance. Correct. Outliers can significantly impact the performance of certain algorithms by scaling features. Outliers are less likely to dominate the distance calculations or gradient updates, leading to more robust model training. Scaling helps mitigate the influence of outliers by bringing them closer to the rest of the data. Points. B. Outlier mitigation. Correct. Gradient descent algorithms rely on the calculation of gradients. Unbalanced scales in features can lead to very large gradients for features with larger scales, causing numerical instability and potential divergence of the optimization process. Scaling helps stabilize these gradients and ensures smoother convergence, improving the reliability and efficiency of gradient-based algorithms. C. Numerical stability in gradient descent. Correct. As all the above choices are correct, this is the correct answer. Feature scaling addresses all these issues, improving model performance, mitigating outliers, and ensuring numerical stability. D. All of the above. D. All of the above. Feature scaling techniques are applied to bring different features to a similar scale, helping various algorithms perform better. Standard scalar, min-max scalar, robust scalar, and normalizer are common techniques, each having its strengths and limitations. Many machine learning algorithms are sensitive to the scale of features. Algorithms like k-nearest neighbors, support vector machines, and gradient descent-based algorithms e.g. linear regression. Logistic regression benefits significantly from feature scaling. Outliers are extreme values in data that can disproportionately influence model training. Feature scaling can help mitigate the influence of outliers by bringing them closer to the rest of the data points. Numerical stability refers to the property of an algorithm or computation to avoid errors or inconsistencies due to the representation of numbers. Feature scaling contributes to numerical stability by ensuring gradients in optimization algorithms are well behaved. Gradient descent is an optimization algorithm used to find the minimum of a function by iteratively updating parameters in the direction of the negative gradient. Feature scaling helps gradient descent converge more smoothly and reliably. Convergence refers to the process of an algorithm reaching a desired solution or state. Feature scaling contributes to convergence by improving the stability and efficiency of optimization algorithms. 1. Image classification pixel values. Image pixels usually have different scales, so scaling can help improve the performance of image classification models. 2. Customer segmentation. Income, spending habits. Customer data often involves features with vastly different scales, e.g. income and spending habits. Scaling can help ensure all features are considered fairly during segmentation. 3. Fraud detection. Transaction amounts, time intervals. Fraud detection models often involve features like transaction amounts and time intervals. Scaling can help prevent large amounts from overshadowing other important factors. 4. Natural language processing. Word embeddings represent words as vectors, and their dimensions can have different scales. Scaling can help improve the performance of NLP models. 25. 5000. 35. 1000. 45. 2000. Suppose we have data with features age and income. Income has a much larger scale than age. Without scaling, a model might give much more weight to income, ignoring the influence of age. Standard scaler transforms each feature to have zero mean and unit variance. After scaling, both features will have comparable scales, allowing the model to consider both features more fairly. Which of the following statements about sklearn, preprocessing, scale is true? A. It scales data to a fixed range, typically between 0 and 1. B. It centers data around 0 and scales it to unit variance. C. It only scales features with non-zero variance. D. It can be used for both feature scaling and target scaling. E. All of the above. False. This describes min-max scaling, not standardization. Standardization scales data to have a mean of 0 and a standard deviation of 1. Not a fixed range. Normalization. True. This is the core function of sklearn, preprocessing, scale. It performs standardization by centering data around 0 and scaling it to have unit variance. Standardization. True. Standardization involves dividing by the standard deviation. Features with 0 variance will have a standard deviation of 0. Dividing by 0 is undefined, so it will not be scaled. This is a side effect of the scaling process, not a specific characteristic of the function itself. Standardization. True. Sklearn, preprocessing, scale can be applied to both features and target variables as long as they are numerical. It is a general-purpose scaling technique that can be used in both cases. Machine learning algorithms. True. All the above statements are true, as demonstrated in the explanations above. Answer. E. All of the above. Feature scaling is a preprocessing technique that transforms features to a common scale. It addresses the problem of features having different ranges, which can negatively impact the performance of certain machine learning algorithms. Consider a dataset with features like age ranging from 18 to 80, income ranging from 10,000 to 1 million, and height ranging from 1.5 to 2.0. Using these features directly, algorithms like k-nearest neighbors or principal component analysis may give more weight to income, as it has a much larger range, even if age or height are more relevant for the prediction. Feature scaling is commonly used in image processing to normalize pixel values for better accuracy. In image recognition tasks, standardization is a type of feature scaling that centers data around 0 and scales it to unit variance. This means features have a mean of 0 and a standard deviation of 1. It is often used in algorithms that assume features have a standard normal distribution or are sensitive to scale. Imagine a dataset with age and income features. After standardization, the mean age and income would become 0, and the standard deviation of both features would be 1. Standardization is frequently applied in machine learning models like linear regression, logistic regression, and support vector machines to improve their performance and stability. Normalization scales data to a fixed range, typically between 0 and 1. It is often used when the distribution of the data is not important or when algorithms are sensitive to the scale of features. Min-max scaling is a common example. Using min-max scaling, Age could be scaled from 0 to 1 by subtracting the minimum age 18 and dividing by the range 80 to 18. Income would also be scaled to the same range. Normalization is useful in image processing when pixel values need to be constrained for specific algorithms. Min-max scaling, also known as normalization, rescales data to a specific range, typically between 0 and 1. It subtracts the minimum value of the feature and then divides by the range of the feature. Imagine you have a dataset with a feature salary ranging from 1,000 to 10,000. To scale it between 0 and 1 using min-max scaling, you would subtract the minimum 1,000 from each salary value and divide by the range 1,000, 9,000. The result would be a new salary feature ranging from 0 to 1. Min-max scaling is commonly used in image processing, where pixel values need to be rescaled to a specific range. Robust scaling is a type of scaling that is less sensitive to outliers than standardization. It centers data around the median and scales it by the interquartile range IQR. Imagine a dataset with income ranging from 1,000 to 10,000. But there's an outlier with an income of 1 million. Standardization would be heavily influenced by this outlier, while robust scaling would be less affected because it uses the median and IQR instead of the mean and standard deviation. Robust scaling is beneficial when working with datasets that contain outliers, as it provides a more stable scaling approach compared to standardization. Feature scaling is crucial for many machine learning algorithms. It can prevent features with larger ranges from dominating algorithms and influencing the results disproportionately. In a linear regression model, if one feature has a much larger range than others, it might have a stronger impact on the model's coefficients, even if it's not the most important feature for prediction. Scaling features before training machine learning models like logistic regression and support vector machines can improve their performance and stability. Distance-based algorithms, such as k-nearest neighbors, rely on the distance between data points. If features have different ranges, distances are distorted, leading to inaccurate results. Imagine two data points with features age ranging from 18 to 80 and income ranging from 10,000 to 1 million. Without scaling, a small difference in income can create a larger distance than a significant difference in age, even if age is a more important factor for the classification. Gradient descent algorithms, used in neural networks and other models, can converge faster and more efficiently if features have similar scales. Scaling features can help avoid slow convergence or oscillations during training. Imagine a neural network with features age and income. Without scaling, the gradient descent algorithm might take longer to converge because it needs to adjust weights for both features with significantly different ranges. Neural networks are sensitive to the scale of inputs, as it can affect the activation functions and backpropagation process. Feature scaling is often essential for training neural networks effectively. In a neural network, if the inputs have a large range, it can cause the activation functions to saturate, leading to vanishing gradients and making it difficult to train the network. Dimensionality reduction techniques, such as principal component analysis (PCA), often assume features have similar scales. Scaling features ensures that all features contribute equally to the reduction process. In PCA, features with larger ranges might have a greater influence on the principal components, even if they are less important in the underlying data structure. Scaling features ensures that PCA captures the most important components, regardless of the feature range. You are building a machine learning model to predict housing prices based on features like size, location, and age. The data has a skewed distribution with outliers. Which sklearn preprocessing method would you use to transform the features to a more Gaussian-like distribution and improve model performance? A. Standard scaler. B. Min-max scaler. C. Robust scaler. D. Power transformer. A. Standard scaler. Standard scaler scales data to have zero mean and unit variance. It doesn't directly address skewed distributions or outliers. While it helps normalize data, it might not make the distribution closer to Gaussian. False. B. Min-max scaler. Min-max scaler rescales data to a range of 0 to 1. It also doesn't explicitly handle skewed distributions or outliers. Similar to standard scaler, it helps with normalization but doesn't ensure Gaussianity. False. C. Robust scaler. Robust scaler scales data using the interquartile range IQR, which is less sensitive to outliers. It aims to mitigate outlier influence but doesn't guarantee a Gaussian-like distribution. False. D. Power transformer. Power transformer is the most suitable choice in this scenario. It applies a power transformation box Cox or Johansson to the data, effectively transforming skewed distributions to a more Gaussian-like shape, thus reducing the impact of outliers and improving the performance of models that assume normality. True. Consider a feature house size with a skewed distribution. The following code demonstrates how power transformer can transform it to a more Gaussian-like distribution. Python. From sklearn, preprocessing import power transformer. Import numpy is np. Data np. Array 1000, 1200, 1500, 1800, 2000, 2500, 3000, 4000, 5000, 10,000 skewed data. Point power transformer method Johansson. Standardize true. Transformed data part fit transform data. Reshape 1. 1. Print transformed data. The transformed data will have a more Gaussian-like distribution, making it better suited for models that assume normality. D. Power transformer. Power transformer is the best choice because it directly addresses the skewed distribution issue. It uses a box Cox or Johansson transformation to normalize data, bringing it closer to a Gaussian distribution. Feature scaling. Feature scaling involves transforming features to a common scale. It is crucial for machine learning algorithms that are sensitive to the magnitude of features, such as distance-based algorithms, k-nearest neighbors, and gradient descent-based models. Linear regression. Logistic regression. In a housing price prediction model, features like size in square feet and age in years have vastly different scales. Scaling them to a similar range helps the model learn their relative importance more effectively. Power transformer. Predicting customer churn in a telecom company. The minutes used feature might have a skewed distribution. Using power transformer can improve the performance of a logistic regression model predicting churn. Gaussian distribution. A Gaussian distribution is a bell-shaped distribution. Many statistical methods and machine learning algorithms assume data is normally distributed. Gaussian for better performance. Power transformer aims to transform data closer to this distribution. Linear regression models generally perform better when features are normally distributed. If a feature like income is skewed, power transformer can help improve the model's accuracy. Predictive modeling, feature scaling, and specifically power transformer can significantly improve the performance of predictive models. By addressing skewed distributions and outliers, it enhances the model's ability to learn patterns from the data. In a fraud detection model, financial transactions might have skewed distributions. Power transformer can help a model, e.g., random forest, learn to distinguish fraudulent transactions more effectively. Outlier handling. Outliers can drastically affect the performance of machine learning models. Power transformer, by transforming the data to a more Gaussian-like distribution, reduces the impact of outliers on model training. In a customer segmentation model, some customers might have unusually high purchase amounts. Power transformer can help ensure these outliers don't disproportionately influence the segmentation process.